So let's start today on our vortex panel method. So I just want to go over a little bit on the questions we have on the wingtip device. So let me just work out a similar question. Maybe that will serve as an inspiration for you to work on the problem set. So one of the wingtip device that actually is quite popular is winglets, right? So today let's actually consider a strange type of winglets that is not exactly on the wingtip but slightly downstream of the wingtip. All right, so let's think about having an additional set of aerodynamic surfaces, let's say a split wingtip, but moved a little bit downstream of the actual tip of the wing, right? So what happens is that, okay, so if we have a concentrated vortex, let me use red to represent the vortex. If we have a vortex coming from the wingtip that hits exactly on the junction of the two split winglets, all right, what actually happens? Right, we know that for a winglet to be producing a benefit, the upper side and lower side of the winglet has to produce opposite lift directions, right? They have to be opposing the swirl, right? I mean, if the flow goes around the vortex like this, the winglets has to oppose the swirl of the flow, so that it needs to produce a lift in the direction over here on the upper side and create a lift in this direction on the underside, right? As a result of this, what is the vortices coming out of the winglet? Well, the vortices coming out of the winglet, there is a one wingtip vortex over here, there is a one wingtip vortex over here, and because the lift changes sign, there is another vortex coming out from here, right? Okay, so now if we draw a control volume, if we perform a control volume analysis, if we draw a control volume around this winglet, what is the total influx of, what is the amount of, what is the integral over the inflow part of the control volume surface of omega dot n ds, right? The inflow part is basically upstream of the winglet. The only non-zero vorticity over there is the intersection of this concentrated single wingtip vortex with this surface of the control volume, right? So the upstream integration would be just equal to the strength of this vortex. Agreed? Okay, and then if you now think about the outflux, right, the intersection of these three vortices with the outlet portion of this control volume, what happens is that the integral over there has to be the same. Okay, which means the amount of circulation, let's say this circulation is gamma 1, circulation is gamma 2, and the circulation is gamma 3. Okay, the summation of this has to equal to gamma. What is the reason for that? The reason for that is if you draw a contour, let's say a black one is the contour around the winglet, then the circulation around the black one, according to Stokes' theorem, is equal to the integral over a surface that fills this contour. And no matter if this surface fills this contour from upstream of the winglet or from downstream of the winglet, right? The Stokes' theorem tells us the integral has to be the same, which is equal to the circulation on this black contour. That means the influx of vorticity has to equal to the outflux of vorticity, right? Or gamma has to equal to the summation of the circulation of these three vortices. So what does the winglet actually do? Is spreading out this concentrated vortex into 3 discrete vortices, right? Assuming the lift per span on the upper side and lower side of the winglet are constants. All right, does it make sense? Yes?
So there's no real benefit to spreading it out to 3 vortices?
Good question. Is there any benefit of spreading out the vortices? In this case, yes. So if you remember, like the flow around these concentrated vortices has high velocity, right? And by Bernoulli's, high velocity regions has low pressure, right? So that's low pressure. High velocity means wasted kinetic energy. Low pressure means if you do a control volume analysis of the momentum, it creates drag, right? By spreading out the vortices, right, if we're able to reduce the magnitude, if we're able to split gamma into all of 3 of them are smaller than gamma, then you're actually spreading out this, by spreading out vorticity, you are reducing the total amount of kinetic energy in the flow field and reducing the total amount of low pressure, okay, in this region. Yes?
Is there any other relationship between the 1, 2, and 3 gammas? Like are the 2 on the ends related, or is it like completely dependent upon the problem?
So you're saying like are these 2 like?
Yeah, like is there any other relation other than they add up to gamma?
So in this case, no. It depends on the lift per span on the upper side and lower side, right? So here you have 3 variables and you have 1 equation. So that reduces 1 degree of freedom. You have 2 degrees of freedoms. These 2 degrees of freedoms can be manipulated by changing how much lift the upper side and lower side actually generates. Yeah. Yes?
So what is the difference then between putting the winglet behind or on the wingtip?
What's the difference between putting the winglet behind and on the wingtip, right? So in this case, from the downstream flow point of view, there is not much difference. Okay, the difference there is difference from a structural loading perspective in the sense that if you put the so you are spreading out the forces. Like what you can think about is the influence of the vortices on the lift per span on these faces are going to be different if you put this winglet exactly on the wingtip. Okay, so the forces are going to be different. But if you're able to shape the angle of attack of the winglet so that the circulation coming out of these 3 concentrated vortices are the same, then from a total induced drag point of view, there is no difference. Right, but the forces on the different surfaces can be different. Yeah.
The other thing is, you have 3 vortices, but that's assuming that there is no taper in the winglets, right?
Yes. So in reality, what happens is that this concentrated vortex is not going to be a single vortex. There is a spread of vorticity right along the wing. There is also a spread of vorticity on this span, right? So what comes out is almost it's a 3 surfaces of vortices coming out. Yeah, but these 3 locations would be where the vorticity would be most concentrated. Yeah, any other questions? Okay, so today we are going to continue to work on vortices. In the last lecture, we started thinking about the superposition of a uniform flow field with a vortex or a number of vortices, right? So today we're going to exercise that and figure out how do we construct a collection of vortices that when we add all of these vertical flows with a free stream, we get the flow around an airfoil exactly. Okay, and after we do that, we then compute the pressure on that flow field to figure out what forces the airfoil would get. Okay, so let's first think about numerically what is the effect of one of the vortices on the other locations of this airfoil. Okay, so let's imagine we number all of these vortices gamma 1, etc., all the way to gamma n, right? And the induced flow of gamma 1 on this location, right, is actually equal to the gamma 1 divided by I would say delta x squared plus delta y squared, where delta x and delta y is the distance between this point and gamma 1, right? Maybe I should say delta x1 and delta y1 because we are looking at the distance between this point and the first vortex. And if it's and this is the multiplier, and the velocity is a vector field, and the x velocity is proportional to minus y, right? Minus delta y. And the y velocity is proportional to delta x. So this is the flow field induced by gamma 1. Okay, and now if we have a collection of vortices, we need to sum them up. So instead of 1, we just look at, we change the index from 1 to I, right? And we sum them up over I goes from 1 to n. So that is the flow field induced by the collection of the vortices. And then we add this up with u infinity x and u infinity y. So then this is the whole flow field, right? Okay, and in order to figure out how strong each of these vortices are, so everything in this equation is known except for the strength of gamma I, right? We have n unknowns. So in order to solve them, we need to say something about this velocity field. And one of the things we can say is that at n points, and conveniently we can just choose these n points to be the n location of these vortices, that the flow should have 0 velocity in the normal direction of the airfoil, right? Or the flow has to be tangential to the surface of the airfoil. Okay, so in some other sense, if this is my velocity, ux and uy equal to this linear superposition, then what I can say is ux dot with nx plus uy dot with ny has to be equal to 0 at n points on the airfoil. That gives me n equations we can solve for the n variables, right? Well, unless these equations are linearly dependent, in which case we need another equation. And we're going to see that these equations are actually linearly dependent, and we need one additional condition. That's the Kutta condition, in order to close these equations and solve for these gammas. So let's actually go into a Python notebook. I think, so all of you are familiar with Python, right? I think one of the classes, you must have taken classes that at least you can read Python code. So what I'm going to do is I'm going to make an example geometry, not like an actual airfoil, but I'm going to make a circle or ellipse to make it easier for me to compute the xy locations and nx and y. So let's make, let's say 10 points on the ellipse, okay? And the angle, let's linear space 0, 1, actually 2 pi, n plus 1, and I only keep the first n points, so that 0 and 2 pi are actually the same points, right? So let's just, oh, it actually suggested me to do this. That's ideal. So let me just plot x and y, make sure that's actually what I want. Okay, that's fine. Oh, I think I didn't, from PyLab, import all. Otherwise, it's going to, all right. Actually, I want x to be cosine, y to be sine. So that makes the trailing edge to be the first point. That makes things a little bit easier. So actually, let's make it the ellipse of aspect ratio equal to 2. So I'm going to get a ellipse like this. All right. And then the next thing I need to compute is my normal. My normal in the x direction is actually cosine s, and y is equal to sine s. But in this case, for the normal, I need to multiply nx by 0.5 to get the aspect ratio, right? So let me just aspect ratio equal to 0.5, so I can change that easily later. All right. Okay. So I also want to make my normal. Well, it's not important to make the normal unit normal for now. So let's just visualize that. Quiver x y nx and y. So that's going to show the direction of the normal, which looks like correct, right? So that's basically my normal vectors. Okay, so the normal vectors are going to be used to enforce the zero normal direction flow condition later on. Okay. Yes?
Again, exactly what are the unknowns you're solving for? Is it the gamma?
Yes, the unknowns I'm going to be solving for is the gammas, right? So that'll, the solution, as we see, is going to depend on the location of these vortices, which is determined by the shape of the airfoil. It's going to depend on the normals, right, which goes into the equations. It also depends on the location of the trailing edge, we're going to see later on. All right, also depends on the free stream velocities. Okay, all right. Okay, so now let's start by looking at what is the induced flow of one of these vortices. So I'm going to say gamma is equal to 0's n. So that's the length, that's the vortices. And I'm just going to say gamma 0 is equal to 0.1. So I'm setting only one of the gammas to 1. Okay, so that's the vortex on the trailing edge. And then what I'm going to do is I'm going to follow this formula to compute only the first part of the induced velocity. So I'm going to say, okay, what is dx? So dx is going to be the location of the vortices. So I'm going to say, so let me actually just help you look at what is x with a non. So basically, this also is can be written as new axis. That basically tells me put another dimension on this x. So essentially, instead of a row vector like this one, it makes x a column vector, right? And if we subtract this row vector with the column vector, we get the matrix, right? So we basically get the rows being different axes and the columns being different minus axes. So that's what I'm going to denote as dx, right? And similarly, dy is also the delta y's. So that gives me the delta x and delta y's I can use in the velocity formula. All right. Okay. So let me say the distance. I'll just say d2, right? The squared distance is going to be equal to dx squared plus dy squared. And I get a bunch of, so because I need to divide by the distance, I don't want to divide by 0. So I will just make it 10 to the minus 10. So that when I divide it, and both dx and dy are equal to 0, so I'm going to be dividing 0 by 10 to the minus 10 instead of dividing 0 by 0. All right. Okay. So then my Vx induced by each of these vortices are going to be minus dy divided by d squared and then multiplied by gamma. Well, so this is going to be matrices. Each term on this matrix represent the induced velocity at one of the vortex locations by one other vortex. Okay, make sense? The different rows represent the different observation points. The different columns means the different vortices that is inducing the velocity. So what we need to do is we need to sum over the different columns, right? Because we are adding the velocity contribution from all the vortices. So summing over the first axis. So the 0th axis is the rows, the 1 axis is the columns. So we are summing over the columns. Now let's actually copy the code over here and look at the velocity induced by this set of vortices, which are 0 except for the first vortex. So we'll quiver Vx and Vy. Let's actually ylim minus 0.5. Okay, so that makes us right. Let's actually do minus 1 and 1. Let's make it a little bit smaller. Right, so this is the velocity induced by this vortex over here. So it actually rotates around to this point, right? And further away it is, the smaller the velocity is. Okay, so now let's actually don't just do it for this single vortex, but do it for all the vortices. So we are looping over all the vortices, and gamma is equal to 0, and we'll set the ith vortex to be a strength of 1, right? And now I should get a series of plots, right? Each one being the induced flow from one of the vortices. So this is the first one. The second one is over here. It induces the flow like this. The third one induces a flow like this. The fourth one induces a flow around this point, etc., etc., right? This is for all the vortices. Make sense? Okay. Now we have completed this term, right? Then we also need to add a free stream contribution. So let's start to do this. Okay. The free stream contribution, let me actually record it as yet another term. So let me actually make an array. So V vortices. Okay, let's actually before we compute the free stream, let's actually compute the normal velocity induced by these vortices first. Okay, so we'll actually not just compute Vx and Vy, we'll also compute V normal, which is equal to Vx times Nx plus Vy times Ny. So, and when we plot each one, let's actually put the Vn in the title to see what they actually looks like. Okay, so for example, this is the first Vn. So on the vortex itself, the first element is on this vortex itself, right? It doesn't induce any normal velocity. On the second point, it induces a negative velocity in the normal direction, right? That's obvious. And in the third point, also negative, but the magnitude is smaller. And the third one, also negative, the magnitude is even smaller. And when you get to, this is the leading edge, it induces a velocity exactly in the vertical direction, so no normal component. And then starting from the lower surface, it induces a velocity in the positive normal direction, right? So similar things you can say about the later ones. So let's actually use an array. So Vn vortices to record Vn vortices and Vn. So let's record all of these normal velocities. And we'll also compute the normal velocity induced by the free stream. Okay, so let's say Vx v free stream is equal to, let's just make it a 1, and let's put a vertical component. Let's put 0.5 as the vertical component. Then Vn free stream would be v free stream 0 times nx plus v free stream 1 times ny, right? Don't need this. So let's actually print to see what it looks like. So this is the velocity induced by the free stream, right? In the normal direction. So remember, I did not make the normal unit normal. I probably should, for this actually helps interpretation a little bit. So magnitude is equal to square root nx. Yeah, so that's fine. So let me actually rerun it and rerun this one to make a little bit easier to interpret. So here you see the normal, basically the normal velocity of the, yeah, so the normal direction of the free stream is equal to 1 at the trailing edge minus 1 at the leading edge, and it's like that. Make sense? Yeah?
I'm confused about what your unknowns are. So your unknowns are the circulations of each vortex, and also the induced flow on each vortex, right?
My unknown is only the gamma i's.
So you know the induced flow?
I don't know the induced flow, but the induced flow are functions of the gamma i's. Right? So what I have is this set of equations. So ux at every point is a linear function of the gamma i's, right? Okay. Uy at each point is also a linear function of the gamma i's. Okay, so ux.nx plus uy.ny at each point is a linear function of the gamma i's.
So really there you have 3 n equations.
I have n equations, not 3 n equations, because at each point I have 1 equation. Right? Yeah. Okay, and I also have n unknowns because the gamma i's are unknowns. So you can express this as 3n unknowns with 3 different set of equations, but it's just easier to express that as n unknowns and n equations, because the relationship between the velocity and the gammas are like they can be analytically written out, right? Okay, right. Good point. So basically at the end, what I want is I want a matrix A times the gammas, gamma 1, gamma 2, all the way to gamma n, and that is equal to a right-hand side. So this is what I'm trying to construct, a set of linear equations that allows me to solve for the gammas. So right now, what I have computed is that assuming each gamma is like, assuming the set of gammas are zeros except for 1 being 1, right? I have computed what is the velocity. So now I just need to perform linear combinations, right, of these velocities in order to set them to 0. All right. Basically, what I have computed is different columns of this matrix A, right? So if you think one of the gammas being 1, the others being 0, and the matrix vector multiplication basically gives me one of the columns of this matrix. Agreed? Okay, so that's that allows me to start the calculation. So basically, Vn vortices are the different columns of this matrix A. So let's make that matrix A. A would be transpose of Vn vortices, because the different rows of the Vn the different entries of Vn vortices are actually the different columns of the matrix A. So transposing them actually makes the matrix A, right? And my right-hand side, basically what I actually have is this plus this equal to 0. And what is this? That's the free stream contributions, right? So that's the normal velocity of the free stream. So that means I need to make it move it to the right-hand side, put it a minus sign. So B is equal to minus of the Vn free stream. Yeah. Okay. So if I solve it, print x, I would get a vorticity distribution. So let me just denote it as gamma. Okay. So now when you print gamma, you're going to see the magnitude is ridiculously high, right? It's 10 to the minus 10 to the plus 14. And if you're able to actually print A, print B, so print the matrix and the right hand side, you're going to see that the matrix has normal like order 1 magnitude. The right hand side also has order 1 magnitude, but the solution has a magnitude of 10 to the 14. So that basically means that the matrix you are solving is numerically singular. Okay, so whenever you solve a matrix and you find that the solution being huge, that means one of the eigenvalues are going to be super small. And you can verify that by just computing the eigenvalues of A. So I actually computes the eigenvalue and eigenvectors. So the 0 component is eigenvalue, and you're going to see, okay, there are two actually there are two eigenvalues that are basically 0. All right. Okay. So this basically promotes us to think about the Kutta condition. So what is the Kutta condition? So we are going to further explain the Kutta condition later as we look at viscous flows. But essentially, the Kutta condition says that on the trailing edge, the velocity needs to be 0. And let me actually explain the Kutta condition by visualizing what is the flow field over here. So I'm going to copy a bunch of code I used to compute the velocity over here, and visualize the velocity induced by this collection of vortices. So right, I don't need the Vn, I still have the figure. Okay, so I'm going to visualize the velocity induced by the this set of gammas that are solved from this equation. I thought I had y lim of y lim of -1 and 1. Let me see, x is scaled is better. Let's see. So let me see, how do I actually, maybe I do y lim and then x is scaled? No. Okay, so let me just visualize that by actually dividing 10 to the minus divided by 10 to the 14 to see what the velocity field actually looks like. Am I doing something wrong here? Let me actually print what is Vx. So this is the Vx. Yeah, so Vx has a magnitude of very large 10 to the 14, and if I quiver with a divided by 10 to the 14, why do I still get this? Let's see. I probably overwrote my x, I think. So let me just rerun the whole thing from the beginning. Okay, so just do the quiver again. Yeah, okay. So here we see the velocity on the surface of this ellipse, right? That comes out from the solution of the system. So what happens is that the velocity, as we have seen, is very large. It's on the order of magnitude of 10 to the 14. And it also rotates over the ellipse like that. And what happens is that if you look at the velocity on the trailing edge, it's especially large, right? And for a viscous flow, what happens is that velocity that's very large at the trailing edge at a sharp point is going to separate. Okay, so basically we are going to say more about this at the viscous flow section, but the flow separation basically puts another constraint on what the circulation, what the vortices, what vorticity distribution on the solid geometry has to be. So let's actually add that onto the set of equations and solve them a little bit differently. So what I'm going to do is I'm going to copy this piece of code, and I'm going to generate another equation. So here we looked at the induced flow, particularly the normal velocity. So what I'm going to do is I'm going to append another Vy, so the y velocity at the trailing edge. So that's just a Vy at the 0th point, right? So we are also going to make another array. Okay, so that's the Vy at the trailing edge. And I'm also going to say Vy free stream at the trailing edge is equal to just the first component, the 0.5, right? That's the free stream contribution to the y velocity at the trailing edge. Okay, so that gives me another equation. Basically, all of these Vy's at the trailing edge contributed by these vortices added together with the Vy from the free stream has to add up to 0. That's basically the Kutta condition, right? So the Kutta condition basically says that if you add the Vy contributed from all the vortices, it should match the opposite of the free stream velocity at the trailing edge. Okay, so now let's actually complement our matrix. We copy this, but complement the matrix with the other equation. So we have this A, but we are going to stack it. V-stack means stack the matrix vertically. So we have the first n rows. We are also going to add another equation, which is another row, right? This other row is I think I called the Vy trailing edge. Okay, so my right hand side also has another component, so it's going to be stacking of Vn vortices with the Vy trailing edge. Okay, so now we have more equations than unknowns. So instead of solve, we have to perform a least squares calculation, and we'll take the solution as the 0th component. So now if we, something's wrong, Vyte is not defined. Did I run this one? Okay, I didn't run this one. Okay. Now I should be able to run this calculation. The velocity does not look right. Oh, okay. So I think I only visualize the velocity induced by the vortices. What I should do is I should add a free stream. So V free stream and V free stream 1 plus Vy, right? So let me look at the combination of free stream and the velocity induced by the vortices. So now what we see is that all of these velocity lies on the tangent direction, right, of these vortices. All right, make sense? So I basically solved the distribution of vortices that makes the flow field conform to this geometry. Okay, so now we know how to do this. Let's actually change our n to be 100 instead of only 10 and potentially get a much better solution. So here's my new discretization with 100 points. And here I don't want to generate 100 plots, so I'm going to comment this out. Oh, actually, I should be running this one, right? I should be running this one without the figures. Okay, and I can just run this one with 100 points. Let me just don't do the title anymore. Yeah, so this is basically my flow field. As you can see, the vector of flow field is the largest over here, and it kind of conforms with the geometry over here. So let me actually remove this one so that we can see it a little bit better. Yeah, so this is how the flow field on the surface looks like. Here is the stagnation point. Here is the trailing edge that we enforce the velocity to be 0, and we have the highest velocity over here. Yes?
In that type of geometry, you have a free stream like going up.
Yes.
So shouldn't the trailing edge be not like all the way to the right, but like on the opposite side of the stagnation point?
Yeah. So I made this geometry just as an illustration. In reality, when we have an airfoil, right, it has a definitely sharp trailing edge. So you're right. For this one, I mean, if you actually run the flow field calculation, the separation point is probably not going to be here. It's probably somewhere over here. And if it's a viscous calculation, there are probably 2 locations of separation, and there is a wake over here. So this flow, if you run a viscous calculation, the flow is going to be different from this. But if you think about if you have an airfoil geometry, we are going to be enforcing the Kutta condition at a known point on the trailing edge. Okay, so finally, let's actually try to compute the pressure, right? Actually, let me actually, before we compute the pressure, let's actually rerun it with a different aspect ratio. Let's just make it, let's make it 12% thickness. Okay, so something a little bit thinner than what we had, and let's regenerate the matrix, and let's don't print this anymore, and visualize the velocity field. The angle of attack might be too large. Let me actually also reduce the free stream to, instead of 0.5 to 0.1. Okay, so that more resembles what an airfoil is going to be like. I think I didn't run this. Sorry. I should run this and then recompute the velocity distribution. So something was wait, don't do the title anymore. Oh, I think I was running the wrong cell. I should be running this cell and then run this cell, which actually computes the velocity with the Kutta condition. So this is the this is going to be the flow field at with a free stream of 1.1, right? With a 10% thickness. Did I? Oh, I didn't change this to 0.1. Sorry, 0.1 and 10% thickness. Okay, yeah, that's what the flow field is like. The stagnation point is actually closer to the leading edge. So but now this is the velocity, right? To complete the last step, we have to compute the pressure field. So if we look at the velocity looks like almost uniformly, actually this is the velocity induced only by the vortices. So let me say, let me just to change the calculation so that when we compute Vx and Vy, we add the free stream. Okay, so we add the free stream in the velocity. And now if you print the velocity field, we're gonna see like everywhere it is actually less than 1. So the reason is that this velocity field computes the velocity at the center of each vortex. So it does not include the contribution from that vortex itself. Okay, so the effect of that vortex is to actually make the velocity immediately inside the airfoil geometry to be 0, right? So the opposite contribution should be added to immediately outside of the airfoil. In this sense, the velocity just outside of the geometry is actually twice of the velocity at the center of that vortex, right? So let me actually draw it a little bit more carefully. So the velocity over here is equal to 0, right? So if there is a velocity at the center of the vortex, then the velocity immediately outside of the vortex should be, so let's say this is my Vx, Vy computed on this vortex. The velocity right outside of it must be 2Vx and 2Vy. Agreed? So that's because we are now adding the contribution of that vortex itself. So now the pressure should be computed by P is equal to half of rho. Let's assume rho to be 1. It's actually minus, right, times Vx square plus Vy square. But now we have to have 2 times Vx and 2 times Vy so that we have the velocity just outside of the surface. Okay, so then let's say Cp, the pressure coefficient, is going to be now the pressure divided by half of rho V infinity square, and V infinity is basically V free stream. Yeah, so that's my V infinity squared, right? And let's actually plot x against the Cp. So that's my distribution of pressure coefficient. And normally when we plot it, we actually invert y-axis. So we normally look at the pressure distribution as a suction being upward and pressure being downward. So this is the distribution of pressure on this ellipse. Okay, so if we compare that with calculation by X-foil, so of course we don't have an ellipse in X-foil, but like we can make an airfoil of a similar thickness. Right here we have a thickness of 12%. So we make a symmetrical airfoil of 12%, and we are at the angle of attack of so my free stream is 0.1 over 1, so it's 0.1 radian, which is roughly 6 degrees. So if I do a calculation of 6 degrees alpha, of course the geometry is different, but what you see is a pressure distribution that's actually quite similar to what we calculated over here, right? Okay, so that kind of completes our lecture of what is the way of going from the geometry, in this case of an airfoil or an ellipse, to the distribution of vortices that we can use to compute what the flow field is like, and then from the flow field, from the velocity field, use Bernoulli's to compute the pressure field. And next lecture we'll go from here and look at what is the consequence of this pressure field, right? And how does the pressure field change as I change my angle of attack and the geometry of the airfoil itself. Yeah, question?
Aren't you missing a term for the pressure because it goes to zero and it should be.
Oh yeah. I'm missing. Yeah, thank you. Yeah, I'm actually so the CP is the difference between pressure here and the free stream pressure, right? What is the free stream pressure? The let's say okay, so P free stream is actually equal to the same thing, but V free stream, well, stream 0. Yeah, so this is my P free stream. So I should be subtracting free stream pressure and then divide by this. So that's yeah, that's what I should get. So at stagnation point, I should get a pressure coefficient of 1, and the minimum suction for this ellipse is about -3 for the airfoil, because the leading edge is actually have a larger radius of curvature than my ellipse. The peak suction is a little bit lower, maybe slightly less than -3. But otherwise, the distribution looks actually quite similar. And the next lecture, we are going to say that especially the gap of pressure between the upper and lower surface should be very similar between these two geometries. So I'll see you on Friday. And the recitation on Friday we're going to learn more about the X-foil and how to do airfoil calculations. All right.